Hello, everyone. Welcome back to CPE 517-WS Digital and Computer System Architecture. This is lecture 1, part 1. We're going to discuss the snooping protocol of last time, but we're going to mainly focus on the diagram of snooping protocol. Okay. So first, some logistics. So we adopted slides from David Patterson, Howie, Sen Nipsey. What the credits goes to the original authors and what the errors are mine. We did some modifications and reorderings, so due to our requirement. A little bit recap. So we mentioned last time, there are chances if you stand on one processor, let's say you stand here, then it's likely you will either grab the bus and try to send something out, like or this, or you can get something back from the bus that is here. Right? We can first try to understand one of the situation. See here, if the status of the cache block is shared, so what we're gonna do is assuming the processor has a read heat, then it's a normal heat. The data will be here. Once it's invalid, and then we see a read miss. So it's also a normal miss because the data is not valid. So we have to place something on the bus in order to request some data. So for the read heat, it's the same thing. We're gonna also read the data directly in the local cache. Nothing would happen, right? So for process, we have if the process, the block is the shared situation, and we do have a read miss, this is a block replacement, okay? And then for the same cache block, if it is modified, but still we have a read miss, that actually implies we have a replacement as well. If we do have the modified and we have a write heat, it exactly means we have a typical normal heat. It's the same as this one. Okay. And then once we have the shared hash block, and then we have a write heat, it means the data we just read, we want to update it. In that case, we place invalidate on the bus. These operations are often called upgrading operations because they do not fetch the data, but just they only change the status. Okay, this will also likely to invalidate whoever holding the data in the situation like processor one, maybe also holding a specific block. So that one gonna be invalidated. Okay, so for write miss, if you have an invalid, you do have a write miss, it's a normal miss, okay? Because that means you don't have the data ready for you to write. If you have a shared situation, however, you still have a write miss, this means you have a replacement because miss only happens when the data is not in cache. If it is the same data and you want to change its status from share to exclusive or modified, in that situation, you typically have a write heat, like what we see here. Okay. So then we move on to this modified, we have a write miss. Why would we have that problem? As we mentioned last time, it is due to replacement because maybe the second cache block that goes to the same cache block wants to be written. So you have to first replace that first one. That is, you have to write it back, and then you load the second one you intend to update. And then the buses are like you standing here, and then processor one give you some instructions. Like for example, if you currently have the block as shared, and then you get a read miss on the bus. So that means you don't have to do anything, right? Because that means the other processor have a read request. If you do have a modified and you have a read miss, it essentially means probably the data you own right now is requested by processor one. So what you have to do is you have to write the data back and then provide the data to processor one. If you have shared, you got to invalidate. It's like this data is shared by you and processor one want to update this data. Then you have to invalidate yourself. So if you have a shared situation, okay, you have a write miss, that essentially means someone attempts to write to this specific block. You have to invalidate the cache block. If you have a modified situation and you have a write miss, that means some other people also want to write this specific cache block. What you have to do is you first have to write back and then change your status into invalid so other processors can move on, right? This is how it works. So by saying that, it actually means that we have different states for different caches and different situations for either processor to send some signal or for the bus to snoop some signal in the bus, okay? For this kind of invalidation protocol, in the write back cache, we snoop every address on the bus. If it has a dirty copy of the request block, we have to provide that block in response to the read request and aborts the memory access. Each memory block is in one state, right? Clean in all caches and up to date in memory in shared, or dirty in exactly one cache that's exclusive or not in any cache, not cached, uncached. Each cache block is in one state as well. So it can be shared, which means this block is being read, could be used by this one or a couple of them. Or exclusive, this cache has only one copy, it's writable and dirty. Or invalid, it means this block contains no data. Read misses causes all the cache to snoop the bus. Writes to clean blocks are treated as write miss. This is very important, okay? So we have this kind of broad diagram, right? But it's really hard for us to understand how different states are transitioning from each other. So right now, let's do the state diagram to see how the cache block transits from invalid to shared and then to exclusive, right? Assuming this processor is, this cache block is residing on the processor that is sending the signal. It could be, if you send a signal saying CPU read miss, then that cache block would change from invalid to shared, okay? If in shared status, you actually have two ways to go. Either you read this block again, so you have a read hate, or you write to this block, so you change this block to exclusive, or you probably have a replacement, which we're gonna talk about later, okay? In the exclusive situation, you could either have a read heat, a write heat, or you could have a CPU write miss. Okay. If you have a write miss, what does it mean? It means you have a CPU replacement, right? Block replacement. Okay. This is what we discussed here. If you have modified and you put a write miss, right? That's exactly what we mean by here. Okay. So that's why you have a write miss here. The reason is like that, what I just mentioned about. Okay. Then in invalid, you also have the chance to directly go to exclusive because you might directly write to that specific block. So you place a write miss on the bus and then you change that specific block into exclusive. Okay. So you might ask, do we have the situation where we can go directly from exclusive to invalid? Yes, we do. But it's not from this CPU. Like this CPU cannot make itself invalid. The invalid has to go from otherwhere, right? And then similarly for shared, you can also go from shared to invalid, but it does not have, it cannot happen from the case that you do it by yourself. And then from exclusive to shared, it's likely, but there are two ways. If you're working on a specific block, it's unlikely because exclusive is, like we call it, a higher priority comparing to shared. So for that specific block, it's impossible. However, if you do a replacement, there another block wants to come in and replace this specific cache block, it is possible. Okay, so by seeing that, let's clean a little bit here. Okay. So we mentioned here from anything go to invalid, it has to from outside, right? From outside of the processor. And then going from exclusive to shared has to be a replacement. So all of them does not really happen for the same cache block and the actively sending the data from that specific CPU. So the next step, we would look into this one. How to change from exclusive to shared, okay? You see the difference is you add this line here, replacement, right? Replacement. And then this is also replacement. We should have changed this here. Okay. For this one, clearly it's situations that when you have the status as shared, then you request another cache block, for instance. So if this is the cache block, they map to the same cache block in the cache. So what we do here is we do replacement from the share to the share, right? So for this processor one, we can replace from this one, like replace this one and put the second one in. So that's how we have a read miss, but we still manage to stay in shared status. Another case is you have cached this one and it's exclusive, but you want to write this, the second memory, this memory block that maps to the same cache block. So what you want to do is you want to read, not changing. So in that situation, what you do is you really just change the status from exclusive to shared. That's also block replacement, right? Comparing this one, you only have 2 more lines here, right? Typical, and this one, I have to clarify that this one is also replacement. Like, you have a write here, but you want to write to another cache block. So it's also possible that we have this kind of write miss. Okay, so it's okay that this CPU have this kind of sending signals to the memory. It is also possible that this CPU is not so lucky. It does not get the arbitration of that bus. So instead, you are actually being a passive participant. That means another processor or other processes, whoever, nobody knows which processor it is send some signal to this processor, okay, to get you some, give you some information. In this case, you could receive quite a bit of information. One case is you get a write miss, okay, or another write miss from here, right? So we see here, did you see here? Write to clean blocks are called write miss, okay? So this is a write into clean blocks, right? The block is clean, I'm writing to that one. Or if I am, this processor 0 is exclusive, that means only this processor would have this copy. So that means other processors who want to write to this specific block definitely will suffer from write miss, right? So they have a write miss here. Then we have to write back. For this one, from clean status to invalid, we really don't have to put a write miss on. We don't have to write back because this is clean block, so there's nothing to write back. Well, from exclusive, you can also go to shared if another processor have a read miss on this specific block. In this case, we got a read miss, and then what we're gonna do is we're gonna write back this cache block to the memory, and then change our status from exclusive to shared. So keep this in mind. Misses happens when the data is not present, except this one. We're writing to the clean block, right? Except this one. So putting all of them together, we have the summary that we can go from invalid to shared, from shared to invalid, and then we can also go from exclusive to invalid, invalid to exclusive. We can also go from exclusive to shared and shared to exclusive. There happened a lot of cases. We already mentioned that go to invalid has to be from bus, okay? Degrading your status also has to go from bus. Basically, it's all degrading, right? So from exclusive to shared, you're degrading your status. And then from shared to invalid, you are degrading your status. Or from exclusive directly degraded to invalid, it's always degrading. So for degrading your status, you have to go from the bus because it's other processor triggers you to degrade it. Otherwise, you're never gonna have to degrade your status, okay? And then for in your own processor, the situation would be either you upgrade from invalid to shared, from shared to exclusive, or from invalid to exclusive, or you stay in this status if you have that situation, okay? So putting them together, we want to see here is that there are quite a bit of cases that we want to consider. We have to first stand as an active participant to this situation. Or if it's passive situation, it's like from the bus, then it's most likely we're going to degrade it or we stay in the same case. In a passive situation, it's very unlikely that we can upgrade our status, okay? Because it's you getting impacted by other people, okay? So putting this together, I think this would be very clear for snooping data structure where snooping protocol where CPUs are communicating through the bus, and the bus is atomic device that only one device, one processor can exclusively arbiter get this device. In that situation, I think the best case would be we focus on the bus, right? So if you see the bus, it can be the bus is occupied this active participant, or the bus is occupied by the other passive participants who is trying to send you some signals, right? So since this is so important, I think we really have to do a little bit of reviewing here. For example, for what I summarized, right? So first, to upgrade the status, right? It has to be from your own, because nobody else would upgrade your status, right? So you opted from invalid to shared, from invalid to exclusive, and from shared to exclusive. And then you can also stay in that status if you do some block replacement or do a little bit of degradation if you have a from exclusive to shared, right? Like this one. Well, in the degradation, majority of the degradation case would come from the bus where people ask you to degrade it, right? So from shared to invalid, from exclusive to invalid, or from exclusive to shared. Well, from exclusive to shared, you have two cases. One is block replacement. Another is really the request from the bus, okay? I think that's it for this state diagram. This is actually very, very, very important. If we have this in mind, it will be very helpful for us to later on look into directory-based and snooping-based examples, okay?